and I'm so glad you made it because logistic growth is one of the easier ideas in BC Calc, especially this unit, differential equations. There's really not going to be a whole lot to it, even though that might be a little bit of a misleading statement, since this video is probably going to end up being 5 hours long. So bear with me, watch it on 2 times speed. It's only 2.5 hours. Okay, so things you need to know you need to know that just population growth has limiting factors, right? We can't just grow unchecked. Populations don't tend to do that in the real world. They tend to have limiting factors. Like if you've been paying attention in your science classes, you might know that there is something called a carrying capacity. And if you have had any instruction on that, then you can basically skip this video, because everything you need to know about logistic growth, you probably learned in science. If you haven't been paying attention in science class, then join me. Okay, here we go. So exponential growth is a great model, but it's a bad model for population growth. All right, so things that could limit a population size would be food source, like how much space there is to live, or if a zombie apocalypse were to happen. What? Huh? Zombie apocalypse? What? Well, a zombie apocalypse, if you think about it, I mean, every time that I watch a movie about zombies, there's one person that gets it, and then they infect some people, and they all infect people, and then they all infect people, until finally we're going to run out of people, right? We can't just continue to grow and grow and grow and grow exponentially. Eventually, there's going to be a leveling off spot when everybody in the world becomes a zombie. All right, so if you think about it in terms of calculus, if we say that the rate of growth of zombies is directly proportional to the number of zombies that are there, right? So dz dt is equal to a times z, so some constant of proportionality a. Well, then dz over z is equal to a times dt, and then if we integrate all that and exponentiate, solve for z, you get that z is CE to the AT, and CE to the AT is an exponential growth function. But that doesn't make a whole lot of sense, because exponential growth just goes unchecked forever. You could end up with an infinite amount of zombies. That's not possible. So it can't happen. There's got to be a tipping point where the rate of growth starts to decrease. Still growing, but it's not growing as fast. So potentially the rate of growth would hit 0 if everybody in the world turned into a zombie, right? So that's a little more realistic. Okay, you got me there. Zombies are not realistic, right? But a lot of population, like fish in a pond, people in a city. I mean, just name it, any population, bacteria in a petri dish, right? There's a limit to how much of a population can exist in one finite area. So population growth is a great application of logistic growth, and mostly we're going to talk about population when we talk about logistic growth. So logistic growth is a model of growth that's defined with the differential equation dp dt is a times p times k minus p, and the biggest idea there is that K is the carrying capacity. You probably heard that word before if you've been paying attention in science. This carrying capacity is the limit of the population. That you can't. That's what the population is going to reach over time. Okay, so if you want to know what that carrying capacity is, it's pretty easy, right? It's what makes dp dt equal to 0. If the population reached K, then you could simply plug that in for P, and you could see that K minus K would be 0, therefore dp dt would be 0. So when you reach the carrying capacity, you don't grow anymore. Okay, so until you reach the carrying capacity, you're still growing. So here's just a different model. There's just all kinds of different models out there. These two, the red one here and the blue one, those are the most commonly seen logistic differential equations. So everything you need to know about logistic growth is tied to the carrying capacity. It is imperative that you know how to figure out what the carrying capacity is. Okay, every question I've ever seen dealing with logistic growth deals with this idea of carrying capacity. So I'll show you a couple of those a little bit later on. So just to show you the difference between an exponential growth model, where the rate of growth is directly tied to how much stuff is there. The more stuff that's there, the faster the growth. You see over here in the green, so dp dt is A times P. That's just saying that the rate of growth is directly proportional to how much population is there. So the higher the population, the higher the growth rate. Where logistic growth, that's the growth rate decreases as this value of P approaches K, because the value of K minus P will get smaller and smaller and smaller, approaching zero as the value of P gets close to K. So you can see just the different shapes of exponential growth and logistic growth. And if you know the shape of logistic growth, you're pretty much good. Most of these problems we're going to solve by just looking at the shape of the curve. Okay, so let's get started. We've got a population of wascally wabbits grows according to the logistic differential equation. dp dt is blah, 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 blah. Given that the population at time zero, given the population at time zero is, whoops, I forgot to write something in there. Let's say the initial population is 10 wascally wabbits. Okay, what is the limit as t approaches infinity of the function p of t? So how are we going to solve this? Well, it's a logistic growth curve. So we know that there is going to be a carrying capacity. So don't think you've got to figure out what the function is, p of t. Don't feel like you got to solve that differential equation for p in order to figure this out. The limit as t goes to infinity of p of t is just code for what's the carrying capacity, right? Because over time, that's what the function is going to trend to. So what is the carrying capacity here for the differential equation dp dt equals 0.02 p times 1 minus p over 350? What's the value of p that makes that 0? And the value of p that makes that work is either 0 or 350. Well, the carrying capacity is not going to be 0, so that means the carrying capacity here is 350 wascally wabbits. So the limit as t goes to infinity of p of t is 350. So what if the initial population of rabbits is anything? What if it was 10? What if it was 370? What if it was 1,000? What if it was 1? What is happening to this curve as we trend to infinity? Well, it's always going to be trending towards the carrying capacity. If you're above the carrying capacity, the wabbits will die off. It's kind of sad. But they're going to trend to the carrying capacity. If you have start below the carrying capacity, that's what you're going to trend to. You will always trend to the carrying capacity. So here is a slope field for a logistic growth curve that here is in green, where the carrying capacity here is 100. I've drawn a couple of solution curves starting at different values. So like I said, if you start above the carrying capacity, like here at 120, the function, the curve, the shape is going to be trending toward the carrying capacity, decreasing to the carrying capacity. If you start at 80, a lot closer to the carrying capacity, you're going to be not growing really fast, but you're going to be trending to 100. And if you start down here at 20, of course, you're going to be growing pretty rapidly, but then that tapers off until the growth rate reaches 0, the closer you get to the carrying capacity of 100. So really, it's all about shape of the curve and knowing how to find the carrying capacity. All right, so it doesn't matter what the initial condition is, the logistic growth always approaches carrying capacity, and the logistic curve is always increasing if you start below the carrying capacity, and the curve is always going to be decreasing if you start above the carrying capacity. And here's like the reasons why. The value of dp dt, the slope, is going to be positive if the value of P is smaller than K, and the value of dP dt is going to be negative if the value of P is greater than K. All right. So another question that you're going to need to know how to solve is, when is the rate of growth the fastest? So when is the rate of growth the fastest? It's kind of easy to think about that. It's kind of logical, because if, say, a rumor was spreading around the school about Mr. Morris and his connection to organized crime, when does a rumor grow the fastest? Well, I mean, it kind of makes sense that the rumor's going to grow pretty fast until half of the population hears about it, right? Because as soon as half of the population hears about it, I can't find as many people to spread this rumor. It just, people have already heard it. They're like, where were you? I heard that last week. You're behind the times. It's just kind of making sense. So let's look at maybe the mathematics behind that logic. So if we consider the graph of dP dt, but we graph where the value of P is the x-axis and dP dt is the y-axis, it will always look like this upside down parabola, right? dP dt is always going to be an upside down parabola. Some things I know about parabolas are they're symmetrical, okay? So if I know the two x-intercepts, I know that the highest spot of this downwards parabola, the vertex, is going to be halfway between the x-intercepts. So if the x-intercepts are 0 and P, halfway point happens at P divided by 2. So half of the carrying capacity. Sorry, that should be half of K. So at half of K, that is when the rate of growth is at its maximum. All right. Another way to think about this is that looking at the graph of dP dt, if dP dt is increasing, that means the function is concave up, because we're saying that dP dt is increasing. So we're saying that the second derivative is positive. And if dP dt is decreasing, so what's happening after that halfway spot of K, that means the curve is concave down. Okay, so if there is a change in concavity, that's the inflection point. So half of the carrying capacity is always going to represent the inflection point on the graph of P of T. Okay, so take what I just said with a grain of salt, because most of the logistic growth curves you see are going to be P times K minus P, or something of the like. But that's not to say that every logistic growth curve is going to look exactly like that. It's just most of the ones you're going to see are going to be in that form. So the half of the carrying capacity is usually the spot of this fastest growth rate. But what is actually true for all cases is that the halfway point of the two x-intercepts of dP dt, let me travel back up here. Let's say the two x-intercepts aren't 0 and K. What if it's 2 and K, right? So it's not, the halfway point between 2 and K is not K over 2. It's just halfway between the two values of P that make the slope equal to 0. You're not going to see that a whole lot, but I just want to make sure to tell you, because that is the mathematical truth. I want to be mathematically righteous here. So what is always true about the inflection point of the logistic growth curve is that it's always halfway between the two y values that make the slope equal to 0. Okay, so let's look at another example here. Good to see more examples. Number of students in a cafeteria is modeled by the function P, satisfies the logistic differential equation. dP dt equals blah. You see it there. All right, T is measured in seconds. P of 0 is 25. So the initial condition is 25 students. What is the greatest rate of change in students per second of the number of students in the cafeteria? So we want to know what the greatest rate of change is. Well, where is the greatest rate of change in a logistic curve? It's always half of the carrying capacity. So if I know what the carrying capacity is, man, I am in like Flynn. So the carrying capacity is when the differential equation is equal to 0. That's pretty obvious, happens at 0 and 2 Hunsky. So 2 Hunsky is the carrying capacity. So the fastest rate of growth is going to happen at half of that. So half of 200 is 100. So that's my answer. Except it's not. Because the question wants to know, what is the rate of growth? What is the rate at when the rate of growth is the highest? So we need to evaluate dp dt when p is 100, which you can see here is 50 students per second. So be careful. The ideas here are simple, but sometimes the questions can flip you around. So if the question was asking for what is the population when the rate of growth is the fastest, my answer would be 100 students. But the rate of growth that is the maximum, I have to sub 100 back into the function for dp dt. So just be careful to read the question thoroughly and understand what you're looking for. All right, last one. We're going to go rapid fire here. I've got a population of roadrunners that is modeled by this differential equation. And this is just a warning shot here. This is not what we're typically used to. This is not P times K minus P. Note here we got a little bit of a monkey wrench thrown in here. So the slope field tied to this differential equation, you see it here. So if P of 0 is 5, what is the limit as t goes to infinity of the function? Well, if P of 0 is 5, I'm starting at 5 and I'm going to trend up and level off at 12. 12, you might note, is the carrying capacity of this dp dt logistic differential equation. So the answer to number 1 is 12. Well, what if the initial condition is not 5, but what if it's 16? What if it's above the carrying capacity? Well, I know that if I can draw in, okay, I'm going to draw in the solution curve if P of 0 is 16, and it's going to trend again to 12, the carrying capacity. All right, so, all right, number 3. Given that P of 0 is 5, what is the value of P when the population is growing the fastest? Well, if P of 0 is 5 and I am growing and leveling off at 12, does that mean that it's just half of that? So 6? Not in this case, because the two values of P that make dp dt equal to 0 are 4 and 12. So I need the halfway point between 4 and 12, which is 8. Will the curve reach 8? Yes, because I start below 8 and I'm going to be increasing. So what's the value of P when the population is growing the fastest? If P of 0 is 5, it's 8. Number 4. What if P of 0 is 9? What is the value of P when the population is growing the fastest? Well, it's 8, isn't it? Because if the initial condition is at 9, we're not going to hit 8. The population is never going to be 8 because we're going to be rising from the initial condition of 9. So the fastest growth rate is at 9 because that growth rate is just decreasing if you are above that halfway spot. If P of 0 is 5, what are the values of P where P is concave up? Well, concave up, that's that shape of the curve where it's growing and then it starts to tail off. So that's going to happen between 5 and 8 because 8 is that inflection point of the curve. All right. Number 6, if P of 0 is 16, what is the limit as t goes to infinity of dp dt? Ooh, a little bit of a twist there because you wanted to say 12, but no, we're finding the limit as t goes to infinity of the slope. So what happens to the slope at infinity of a logistic growth curve? It approaches 0. So the limit as t goes to infinity of the slope is 0. Woo! That was rapid fire. Here we go. So let's kind of wrap it all together. What have we learned? Logistic growth differential equation can be modeled these two different ways. They're both representative of some downwards facing parabola. The most important feature of a logistic growth curve is figuring out what the carrying capacity is. So what values of P make the slope equal to 0. And then the spot where the logistic growth curve grows the fastest is when P is half of the value of the carrying capacity. In most cases, like I said, in most cases you're going to see. So next time we're going to talk about how to solve a differential equation, any differential equation that you can separate anyway. There's lots of differential equations out there that you won't be able to solve with this next method that I show you. But that's what we're going to talk about next video. I'll give you some bonus coverage here in a second. So I'll see you then. Peace.